cloud. So the first problem here on this new page, whatever I said, page 4, is find the area of the rectangle. And it's almost exactly the same in terms of structure as the one that we did last class, but it's good to have a second look at this, right? And so what we want to do is we want to use our knowledge of triangles to get the job done, right? So our knowledge of triangles just boils down to this idea that the area of a triangle, oops, got to turn the pen on. Is half the base times the height, right? And so what we're looking at here again, kind of rehashing some of the stuff we talked about, but I'm looking at two congruent triangles. So what that means is that the area of the rectangle is going to be two of the areas of the triangle. And if the area of a triangle is half the base times the height, and we want two of those, 2 times a half, so the product of the 2 and the product of the half would be equal to 1, you'd get a result of just base times height. All right. So if we have a base and we have a height, then we have what we need. All right. So I have a height. Let me use a highlighter for that. I just need the base, right? Now, opposite sides in a rectangle are congruent, which is one of the reasons why we talked about those properties. This side is congruent to this side. So if I figure out one, I've got both, right? This side here is congruent to this side. So again, if I have one, I have both. So I know that this has to have a dimension of 3 or a length of 3. And we also know that regardless of the orientation of the rectangle, they said it's a rectangle, so we know all the properties of rectangles are in play here. We know that there's got to be a right angle, right? So I'm going to use a squared plus b squared is equal to c squared. And the only thing you got to be careful about, it happens all the time in math. We're using b for one thing down here, and we're using it for something else up here. These are two different b's. This is b as it applies to the Pythagorean theorem. This is b as it applies to the half the base times the height, or in this case, base times height formula. Right. So you just got to keep that in mind. It's not the same b, or not necessarily the same b. Right. So I'm looking for this side here, which I could call b if I want, but I'm going to call it a. So a squared plus 3 squared is equal to 10 squared. So a squared plus 9 is equal to 100. And a would be, or a squared. If I subtract the 9 from both sides, it's going to be equal to 91. And so just quick subtraction. Sorry, I feel a sneeze coming on. Lost it. I was going to do the quick mute, sneeze, and then unmute deal, but not that it would have been too crazy to sneeze on a live Zoom. It's just my sneezes are like abrupt and scary. So if you're not ready for it, you might have gotten a little alarmed, let's put it that way. So anyway, take the square root of both sides to get the a alone, and you get a is equal to the square root of 91. All right. So it's a squared plus 3 squared is equal to 10 squared. So a squared plus 9 is equal to 100. Knock the 9 off of both sides. I gave you a 91. And now we have the square root of 91, which if we can break down, we should, but look for factors of 91, 91 divided by your popular perfect square values. Well, 1 wouldn't help, but 4, no, 9, no, 16, no, 25, 25, no, 36, No, and then once you get more than halfway to the 91, you stop trying because it's not going to be a product of the perfect square. So it might be factorable, but its factors won't involve a perfect square. All right, so radical 91 is where we would leave that, but now that's the base. So the 3 would be the height. So in my area of a rectangle formula, base times height would be radical 91 times 3, or we would just write that as 3 radical 91. And it would be square units, but they didn't give us any units here, so I'm not going to lose any sleep over putting the units down or not putting the units down. But technically, if you wanted to include the units, it would be unit squared. So you're not really saying too much of anything except for knowledge that they are square units. It's more like academic than practical. If I can get this fit, of course I can. All right. So that was the case of the rectangle. In the case of the trapezoid, I got the labeling right for a change. Again, we're using our knowledge of triangle areas. So what I would be looking for is this triangle, if I can get a right angle, this triangle plus the rectangle in the middle, plus the other triangle. Trying to sync up my speaking with my writing. Not quite, but I guess I'm going to leave it. All right, so I'm just going to put that little right angle marking there, make it apparent, or I'm going to say obvious. It's not always obvious, but it's acknowledged that it's a right angle, regardless of the quality of the diagram. Put the little box there. All right. So this whole distance here, I'll zoom back out in a sec for those still looking at the previous example. Right. This whole distance here is 9.8. Right, that whole shebang. So from here to here, we have 4.5. Now, in a trapezoid, opposite sides are parallel. In an isosceles trapezoid, the legs are congruent to one another. So this side has the same length as this side, right? But what happens is when we drop an altitude, so when we drop a perpendicular here and here, we're creating two parallel lines. This is going to be parallel to this. We already know that these two are parallel. I'll just put one arrow there. So what we just created was a parallelogram, right? Parallelograms. Oh, hold on, I'm sorry. I leaned back and now I'm going to hit it. Right. So in a parallelogram, the opposite sides not only are parallel, but they're congruent, right? Add to that we now have a right angle. This inner figure is going to be a rectangle. All right. So everything that goes with being a rectangle is in play. Right. So opposite sides are congruent and all that good stuff. Right. But we knew that from being a parallelogram anyway. The rectangle part of it's going to allow us to apply the Pythagorean theorem. Right. So I know now that this side here has to have a length of 4.5. Right. If I do a quick 9.8 minus 4.5, we get 5.3. 5.3 split among the two fringes there would give us two little line segments here. Now the numbers aren't going to be pretty, so we're not going to expect our answer to be in simplest radical form. But this would have a value of 2.65, and this would have a value of 2.65. All right, so we have those dimensions. All right, but we don't know this side here. And that's what we would need to know in order to figure out the area of this trapezoid. All right. So if I take the area of that first triangle, area of a triangle, again, half the base times the height, and I multiply it by 2, so 2 of those area of the triangles, I'll get 2 times half the base times the height, which is going to be base times height, right? But just bear in mind that the base I'm referring to would be this base. And the height that I'm referring to would be whatever this height is, right? Because if I take this triangle here and remove it and flip it around, I would create a rectangle over on this side, right? So I'd end up with a rectangle multiplied, or I'm sorry, a rectangle area added to another rectangle. Right? So that looks pretty messy, so I'm not going to do that in there, right? So long story short, I have to figure out what the length of this side is here in order to make this whole thing work, right? So I think I did the same thing I did last class, and that is I left off one dimension. I wish I could make it through a handout without making a typo. So let's say we know that this leg here is, it really doesn't matter, but I'm going to make it 3. Right. So this is the typo that should be there. All right. So if this is a 3, we have the ability to figure out what that height is, right? That pink highlight. Right? So a squared plus b squared is equal to c squared. I'm working off just this triangle here. All right. So the base, we'll call that a, so 2.65 squared. The height is unknown, so we'll leave that as b squared is equal to 3 squared. And we'll just crunch the numbers there. 2.65 squared isn't something that we would do by hand. So I'll just pop that in. I mean, you can convert it over to fraction if you want, but that's not a very good looking fraction. So we'll just leave it as a decimal. So 7.0225 plus b squared is equal to 9. I think I mentioned this last class, but there is a way to figure out that area, but you'd have to use trigonometry or more complicated algebra. So it's just easier for me to just make up a number. That's why I put 3 there. And that's why I keep forgetting to put a 3 there, because I know that you can do it another way, and I keep losing track of that. All right, so I'm going to take that number away from 9. I'll just tuck in a 9 minus in front of it. So b squared is equal to 1.9775. And then I would need the square root of both sides to get the value of b. So I'll just retype 1.9775. And then we got this disgusting decimal here, but it's irrational, so it kind of makes sense that it would be disgusting. All right, so, but it's not our final answer, so I'm going to hang on to this whole decimal. So 1.406236111104. All right, so now that's the measure of this height here. All right, so we now have enough information to figure out the area of this trapezoid. So I'm going to take the base of 2.65. Right, so I'll work on the 2 triangles first. I'm going to take the base of 2.65 and multiply it by the height that we just came up with, 1.406, blah, blah, blah. Then I'm going to add to that the area of the inner rectangle. Which has dimensions of 4.5 multiplied by that height. So essentially, I'm taking this and adding to it this. And that's going to give me my entire area. All right. So it's like, okay, well, that's a lot to type in. But what you can do is you can set whatever this value is. I have it in Desmos here. I can set it equal to whatever I want. Since that's the height, I'll just say h equals. And now anytime I type in an h, it's going to bring back that lengthy decimal. So I can do 2.65 h plus 4.5 also h. Right? And so the total area of this trapezoid would be that lengthy decimal. And you know, if you're not given any rounding instructions, your best bet is to just put the entire decimal down as your final answer. Now, there are shortcut rules for all this stuff. The issue is they usually involve more than just simple algebra. Simple algebra is not wrong, but simple geometry. Right? We want to keep it just simple. We don't want to get into the world of trigonometry. Right? So yeah, that's just something to keep in mind. But if you recognize the little relationships, you can save yourself a little bit of time anyway. You know, like in the case of the rectangle, base times height. You know, it's like you're taking the two triangles, adding them together, and you're getting the total area. But it just turns out that that's the area of the corresponding rectangle. Same thing happens with the parallelogram. And I've tried repeatedly to draw this correctly, and I'm never successful. I'm going to try it one more time. So if you take this triangle and move it on over here, you never get it to quite fit. But this rectangle here is going to have the same area as the parallelogram. Okay? There's something called Cavalieri's principle that we're going to get to in a little bit. But basically, it's saying that if you have two geometric figures, so in two dimensions anyway, if you have two geometric figures that have the same height, I'm sorry, the same width at every height, then they're going to have the same area. Right? So if I take a rectangle, so I'm going to take this line segment and make it correspond to a rectangle. And I'll just steal this here. This rectangle that I'm producing is going to have the exact same area as that original parallelogram. And the way I know is because their heights are identical. This height is the same as this, right? And their lengths, I'm sorry, the widths at every height are exactly the same. So if I take this length or width, or depending on how your perspective, and bring it up through the rectangle, it's always going to be the width of that rectangle. Right? It never deviates from that. It's always the same. Right? Now, but the same is true for the the parallelogram, I just have to travel along a diagonal movement, but it always represents the width of the parallelogram, right? So they both have the same height and they both have the same width. So why wouldn't they both have the same area? Right. So that's a little bit of the theory without getting into a formal proof. The bottom line is I can do all the crazy work that I did up here, or I can say, well, if the height is 4.5 and the width is 8.2, and these two figures are going to have the same area, then I would just figure out the area of the corresponding rectangle rather than worrying about the parallelogram itself. So the area of a parallelogram is base times height. It's the same base and the same height as that of a rectangle, the corresponding rectangle. So in this case, 8.2 multiplied by 4.5. So I just need to crunch those numbers, and I have it. So 36.9. And again, the units, oh, it froze, lovely. I'm sure it'll come up in a second, but the units are going to be square units. It's just a question of like, okay, are we talking meters? We're talking about inches, yards, whatever. These were not given in terms of units, so you could either put in units squared or you could just leave it unitless, at least for any assessment from me. You know, like you go walking into another class down the line, and I'm sure somebody's going to be very particular about that sort of thing. You know, every teacher's got their own peculiarities. Mine kind of change from year to year. It's the I'm consistently inconsistent, I think is the statement du jour. So anyway, so we're going to apply this information to three-dimensional figures, which is, I think, or it should be interesting, you know. Interesting being the first word of the day. Interesting. And there's a slight chance I used that word already, but that doesn't matter. That's fine. Okay. So the interesting, as in what I'm about to teach you, is the first word of the day. So to find the volume of a three-dimensional object with uniform cross sections, right? So that's something that we're gonna have to wrap our brains around, right? Uniform cross sections. We multiply the area of the base of the object by its height. That last little bit, that's the easy part. Knowing when this concept applies, that's what's challenging. We multiply the area of the base of the object by its height. So if you can figure out the area of the base of the object and you know its height, then you can figure out the volume. But it would have to be an object with uniform cross sections. And it's like, okay, well, how do we know that? Right. So for that, I'm going to take us over to GeoGebra. I think I'm going to do it on the computer. So let me pause the resume recording. So this is a three-dimensional coordinate axis or system of coordinate axes or set of coordinate axes. I like to turn off the plane just to make it look a little nicer. But when you look at a three-dimensional I just lost the term. Environment. That's not the term I was looking for, but that's the one I'm going to live with. What you're looking at is three physical dimensions, length, width, and height, right? So I'm going to turn on the x-axis labels. Same thing for y, so you can see which one is the length, which one is the width. The height should be obvious, but I'll turn on that label also. Okay, did I not turn it on? I must not. I turned it on. I don't know why it's not. All right. Well, anyway, the red is the X, the green is the Y, and the blue is the Z, right? So length, width, and height. So what I'm going to do here, and I'm not going to ask you to do this part, but I'll just show you really quickly what I mean by an object with uniform cross sections. Right. So I'm going to produce a cylinder here. Right. So let's say x squared. You don't. Again, you don't. I'm just thinking out loud here. Plus y squared equals let's say 4. All right. So that's a cylinder. It's an infinite cylinder, which means it goes up and it goes down forever, but it's still a cylinder. If I look down from the top, you can see it's circular. Right. The top-down view is really a good view of a cross section. It would be the topmost part if it were a filled-in cylinder, but it's not. So, but what I can do is I can create a plane. I'll call it z equals 0. Right. So what's happening is I'm taking a plane and slicing through my three-dimensional figure. Right. Where it slices through, see that little area where it cuts? That would be a cross section if we were to lop the top off. Right. But if I go up or down, you'll see that no matter where I go, the size of that intersection never changes. All right. So this little, it looks like an oval, but it's really a circle because from the top down, you change your perspective, it's circular. But from the side view, just to get a perspective going, it looks like an ellipse. It looks oval, right? But no matter where I go, the size of that figure is never changing, all right? So let me see if I can do the intersection and make it pop. They changed the functionality a little bit here, but plane quadric 0, so P and EQ1. Yeah, there we go. All right, I do remember some things apparently. So yeah, that blue dashed curve would be the boundaries of the cross section. All right. So anything in between would be the cross section itself, and you'll see that it's not changing no matter where I go, going up or going down. Its width is never changing. Right. It may seem like it is because of the perspective, but it never is. Right. So that's the idea. Right. Now, it might not necessarily just be a cylinder. It could be any figure that you can think of that would have uniform cross sections. But sometimes, at first glance, it looks like, oh, maybe it won't, but it does. Sometimes you have to rotate the figure, look at it from a different perspective. But the ones that we work with will have uniform cross sections, right? So let me. So now we're looking for volumes of solids with irregular bases. Okay, so it's kind of the rationale behind the methodology on volumes with regular bases is that you can use that information to translate it over to this concept. Right. So first off, we'll start with the area of a polygon, of unknown configuration. Well, I mean, it's part parallelogram, part triangular component, but it's not the easiest thing to work with if you wanted to break it up into triangles. But what you can do, one technique is it's a rectangular approach. I'm not sure what the name is. I probably should know this, but it's never been an issue. Just encase it in a rectangle. Right? So you encase the entire figure in a rectangle. and subtract off the parts that you don't want. So you'd find the area of the overall rectangle and say, all right, well, there are pieces here that I don't want. And it'd be like, well, what are the pieces that I don't want? Well, I don't want this piece, I don't want this piece, and I don't want this piece. So we'd get rid of those. Let me get rid of the highlight. But what I do want is the figure in the middle. So I want all this. I can never. I do my best. Well, anyway, so this is what I'm looking for. This other stuff here, this and this and this, I don't want any of that. Right. So I have this on a set of coordinate axes. So it should be pretty easy to just count boxes to figure out what each dimension is, because each little cluster of points is worth 1 unit. And so since it's a rectangle, the distance, opposite sides are parallel, the distance from side to side will be consistent. It'll be the same from, any point along this figure, right? So we have 1, 2, 3, 4, 5 units along the outer dimension. So that's from top to bottom. And then from left to right, same deal, let's count boxes, quote unquote boxes, from beginning to end. So 1, 2, 3, 4, 5, 6, 7. So that would be a total of 7 units. So this would be what we call an overestimate. The area of the rectangle. We'll call it a rectangle. The area of the rectangle would be 5 times 7. That's going to be way more than I would need in terms of total area. 35 square units. Right. Now, if you're thinking about like, how much money you need to go out to dinner, and it's like, this is all the cash I have. Let's see. Well, the burger is going to cost $12. Well, let's say 15. A drink's going to cost $7. Let's call that 10. And maybe an appetizer will cost like $5. Let's call that another 10. You're 15, 10, and 10. You're at $35. That's more money than you need, going but you're not taking any chances. Right? But if you're accounting for material, you want to have exactly what you need. Otherwise, you're going to have a problem with it. Right? So, because you just think about, how many people do any kind of woodworking or anything like that. But if you want to have roundabout what you need in order to do the job, because you're going to transport the materials, and that costs it's time, effort, and money. Right? So what I need to do is try to get a little bit more precise. So what I'll do is I'll first lop off this triangle here. All right, that has dimensions. We know it's 5 on one side, 1 unit on the other. So this triangle, area of this first triangle, I'm using color coding, so it should be all right. Half the base times the height. You can call either the 5 or the 1 the base, it doesn't matter. 1/2 of 5 times 1. It's going to be 5/2, or you could say 2.5. All right. So then we grab another color, and let's lop off this triangle here. This triangle has dimensions of 2 by 1, 2, 3 units, 2 by 3. Now, coincidentally, it doesn't always play out this way, but this other triangle also has dimensions of 2 by 3. 1, 2, 3. 1, 2. So they're congruent triangles. How do I know they're congruent triangles? Well, side angle side, because these are both right angles. Congruent triangles have the same area. Right? So I would figure out the area of a triangle, 1/2 the base times the height, again, 1/2 of 2 by 3. That's going to give me a result of 3, but 2 of those triangles, 2 times 3 would give me 6. All right. So in all, what I got to do is I got to count for the 35 units that I have in total. I got to knock off the 5/2, and I got to knock off the 6. Right. So you might be better off working 2.5 as opposed to 5/2. Either way, 35 minus, you do it in either order. 35 minus 6 is 29, minus 2.5 is going to be 26.5 units squared. Right. Again, 35 minus 5/2 minus 6, 26.5. Right. So you can do it that way. So manually or in your head, not manual, well, manually, depending on what you define manually as, or in your head. The one thing you shouldn't really have to worry about doing is getting a common denominator and things like that. That's not really necessary. Okay. Now, we have this funky looking prism here, which I created on GeoGebra. Surprise, surprise. I don't think I saved it. All right, let me take a quick look. Might have. Sometimes I save. Just don't ever remember what account I use for this stuff. Yeah, I did actually, shockingly. One second here. Oh, well. Sorry, it always gets either too cold or too warm in here. All right. So let me pause the recording. Okay, so when we're looking for the volume of this prism, we're really first looking for this base area here. I have to figure out what this base area is. And then I'd have to investigate to make sure that that is a consistent cross section throughout the entire figure, so that I could just multiply it by its height. And it appears to be. It's traveling throughout the distance. So for irregular figures, it can be a little trickier to verify these things, but it does appear that if I could figure out the area of this figure, that I'll know the main component of the volume. Right. And so we take it back to what we just did. You look at this figure and compare it to that one, it's got the same configuration. Right. Now, if you look a little closer by the coordinates, this one has a coordinate value of -4. You go over to the left 4 and down 3. This one also has a coordinate value if I go to the left 4 and down 3. So this coordinate value here at B is -4, -3. Right? It's exactly the same. It's just it's scaled a little differently. And if you go to all the other coordinate values, you'll see it's exactly the same. Right? So this here represents the base area of this figure there. So I kind of broke it up so that you could look at it as a single two-dimensional figure, and then as it's part of a larger three-dimensional figure. So all I would really need here is this distance. All right, so if I get the quote unquote height, the area of the base times the height, I'll be in pretty good shape. All right, so now I need some kind of method to make that determination. All right, so the tricky thing is when you get into 3 dimensions, it can be a process. All right, but you're also kind of looking at it from the perspective of, well, maybe I don't have to represent it with an actual height. Maybe I'm coming up with more of a general representation, right? So if I don't know the actual height of a figure, or I don't have the means to figure it out, I can just leave it as h. Right. So I'm just going to call it, for now anyway, I'll call this h. I know the base area is 26.5. 26.5 times h would give me the cubic units that make up the volume of this figure. Right, so if I happen to know, for example, if the height h is equal to 5, then I could say 26.5 times 5. But the benefit of being able to do something like this in what we call general terms is to say, all right, well, what if it's 25 feet? What if it's 30 feet? What if it's 100 feet? I can always have a method by which I can come up with the volume. All right, so this would be a general rule for the volume of the figure. This would be an example of what we call a particular case. So 26.5 times 5, 132.5 cubic units. But if I needed to, on Desmos, for example, and other forms of technology, I could leave it as 26.5 times h and let h be some slider value. So let me just do a new blank graph. 26.5 times h, create a slider, and now I have the ability very quickly to come up with a volume if I wanted to extend my figure. If I wanted to make the room taller, like if I wanted to extend the roof on the house, like how much more volume would I capture? So if I had a height of 5, it would give me 132.5. But what if I wanted to double the height? Then I would be at 265. So now I have the means by which I can come up with the volume no matter what the height is. Right. So it's a more generalized approach to things. Let's see. Oh, okay. Yeah, question.
Professor, that 4.5 over there, does it mean something or just?
That 4 point, I honestly don't, I don't even know what that is. It really kind of tucked itself in there, didn't it? Honestly, that could be the height of this line segment, in which case instead of using 5, I would use 4.5. But I think I might have just accidentally put that in there.
Okay.
Yeah, that was a label from GeoGebra. That I meant to delete that out of there. So just kind of pretend it's not there.
Okay.
So I'm going to go with it. Yeah, because like, for example, you remember that that cylinder problem that we did before. So if I wanted to, I could say pi r squared h in general terms, meaning only coefficients, no numerical values, and leave it kind of flexible so that depending on whatever the height is, I can come up with a new volume. Right? The one that I had on GeoGebra had what we call infinite volume, infinite height, which led to infinite volume. But if I wanted to cap it at 10 feet or 100 feet or maybe only 1 foot, I would have the flexibility to do that using something like Desmos or GeoGebra. Right. So in that problem, if I remember correctly, and I don't, okay, so this was a radius of 4 centimeters. So if I leave it with a variable h, that gives me the flexibility to manipulate the height and determine what all the different possible volumes are. So let's say in this case, I wanted to go up to, I'll call it 20. And then I would know that its volume would be 1005.30, blah, blah, blah. Right. So it's kind of a nifty way of being able to look at these things and not being just one and done problems. They're more flexible.